So the water level, which is again the upper limit from the zone of saturation, is a pretty key feature for understanding the groundwater system. The level of the water level, the level of the water table will be very important for predicting the productivity of a well, for explaining the changes in springs or streams, and for accounting for different fluctuations in the levels of lakes, for example. So the water table level, as you would expect, will also vary pretty greatly from one place to the next. It can go from being 0, in which cases the water saturation is right at the surface, to being hundreds of meters below the surface. So one important characteristic of the water table level is that it varies seasonally, and these variations are actually very closely related to precipitation. So groundwater levels tend to be higher sometime after episodes of precipitation occur. So if you have precipitation, heavy precipitation, and you have an aquifer, which we'll look at later, that through which the water flows really easily, or the rocks above will let the water flow really easily through them, then the groundwater will rise, or the water table level will rise right after the episode of heavy precipitation. So say a few days after, or maybe even a few hours after. So it is tightly related to precipitation. The water table levels are typically monitored constantly by examining the water levels at wells within the area. So the USGS, as well as some local agencies, maintain large networks of observation wells for this monitoring to occur. And using these measurements is how the water level maps can be made, like the one that you're seeing here in the lower part of the slide. So within these maps, like the one you're seeing, typically the well locations are known and different well or water table level measurements are taken at those well locations. After those are taken, we can pretty much make a topographic map of the water levels. So the same way that we make a topographic map based on GPS measurements of the elevation, same thing is done for the groundwater or the water table surface, basically. So the water table will actually typically resemble the shape of the overlying topography, which means that the highest levels of the water table tend to be beneath peaks and hills, and then it starts descending towards the valleys, as it is seen in the picture up here. So you're seeing up here where there's like a topographic high, the water table is also the highest, and as the topography above starts descending towards the valley, so does the water table. Perhaps not at the same gradient, but it's still doing so until it reaches the stream, which is at the point where the water table is 0. So in wetlands, the water table is right at the surface, and then in areas where you have lakes or streams, like the image over here, are places where the water table tends to actually be above the surface. So in this case, water table comes here and it's above the surface, which causes the stream to be the height that it is. So there are some factors that will contribute to the irregular surface of the water table. The fact that groundwater moves very slowly and at varying rates under different conditions will allow water that infiltrates to sometimes pile up before it continues its descent on the way down. And sometimes, though it's a little bit rare, this will allow for the water table levels to maintain or even to grow, even when it has abnormally little, or when there is abnormally little precipitation in the area above. The interaction that there is between the streams and the groundwater system is the basin link for groundwater in the hydrologic cycle. So there are 3 ways in which these components can interact, again, the streams and the groundwater itself. The first way in which it interacts is when streams gain the water from the inflow of groundwater through the stream bed and through the stream banks. This type of streams are usually called gaining streams because they are gaining the water. So in these cases, the water table level is higher than the level of the surface of the stream, as you're seeing in the top picture. The second way in which they interact is when the streams lose water to the groundwater system by outflow through the stream bed and the stream banks. These types of streams are usually termed losing streams because they are losing their water to the groundwater system below. And for this to happen, the water table has to be lower again than the level of the surface of the stream. Some losing streams can be connected to the groundwater system by a continuous saturated zone, like example B, or they can be completely disconnected from the groundwater system by an unsaturated zone in between, like the image here on the letter C. A third way in which the streams and the groundwater will interact is when there is a combination of both types, of both gaining and losing streams. So in this case, the stream will be a gaining stream in some sections, and it will be a losing stream in other sections. This is the case for most rivers. In fact, about 95% of streams are both gaining streams at some point through their course. And as you can see in the image, this has to do both with the geographic location and the total precipitation. This also has to do with things such as seasonal variations or large storms or floods that occur in the area, so some climatic control as well. So the availability of groundwater depends not only on the amount of water stored in the saturated or phreatic zone, but also on the ability of groundwater to move through the subsurface environment. The nature of the subsurface material will have a super great influence in the rate of groundwater movement and also in groundwater storage. So two main factors are especially important when considering the material in which the groundwater is moving or being stored. These two factors are porosity and permeability. So porosity is the percentage of the total volume of rock or sediment that consists of pore or empty spaces. Pores are voids that resemble the openings of a sponge, for example. But pore spaces are also things such as joints or folds, meaning large fractures. They can be cavities that are formed by the dissolution of soluble rocks such as limestone. And they can also be vesicles, which, as we saw in Chapter 4, are voids left by the gases that escape from lava. Permeability is going to be the ability to transmit a fluid through the material. So permeability is key for providing actually the connectivity in between the pores so that an actual movement of the liquid can occur. So in this slide, you see the Snake River Plain in two different maps, as you're seeing here. The top one is going to show you the extent of the quaternary basalt rocks by volume. So you're seeing that higher volumes here on the eastern Snake River Plain versus the western Snake River Plain, which doesn't have very much. And then the second map here, it shows you the type of aquifer system that is prevalent throughout the Snake River Plain. So this is to show you the great reservoirs that even basalt, which is a volcanic rock, not necessarily having grains, can make because of the different porosity and permeability abilities that basalt can have. And again, we'll look at porosity and permeability in a little bit more detail on the next slide, in which rock types are porous and permeable and make good aquifers or reservoirs for the groundwater. It is through pore spaces that water flows through, and also in them is where water is stored. The variations in porosity can be very large, typically in different rock materials. Sediments are commonly very porous, and these pores may at times occupy as much as 50% of the sediment's total volume. Sometimes, however, they can occupy as little as only 10% of the sediment's total volume. And again, these sediments, when I just say sediments, I mean uncemented sediments, so unconsolidated ones, okay? When I mean sedimentary rocks, then they're going to be consolidated, meaning cemented in some way or another. Pore spaces are very dependent on the size and on the shape of the grains, how well those grains are packed, how sorted they are, and also for the detrital sedimentary rocks, what the degree of cementation is between those grains. So, for example, some clay material, which tends to be very fine-grained and well-sorted, if you consider it being relatively well-packed but not greatly well-packed, and also relatively poorly cemented, has as much as 40% porosity within it. So that's kind of like what you're seeing in this material over here. In contrast, some gravels, which are very poorly sorted, typically well cemented, and typically well packed together, may only have about 20% of porosity. So this would be the case over here, where I have gravels, and then in between the gravels I have smaller particles of sand and clay that are filling in the empty spaces. So in these cases where I have well sorting and where I have relatively little cementation, I can get as much as 50% porosity. In other cases where the sorting is not as good, and depending on the sizes that I have, as well as the cementation, the porosity can be a lot smaller. So where the sediments are poorly sorted, the finer particles actually infill in between the large grains, like you're seeing over here. So overall, it is in those cases where the porosity is reduced. Most metamorphic and intrusive igneous rocks, as well as some extrusive igneous rocks and sedimentary rocks that are composed of tightly interlocking crystals like limestone or chert or halite, make voids between the crystals to be negligible. They don't exist basically in these type of rocks. So in these rocks, again, more crystalline looking ones like metamorphic ones, intrusive igneous rocks, limestone, sometimes basalt even, the pores come from different fractures or joints rather than voids in between grains because they are grainless, or even if they do have grains, they're very well connected to one another. So, also as I had said, permeability is pretty key for providing the connectivity in between the pores so that movement of the liquid can occur. Groundwater will move by basically twisting and turning through interconnected openings, and the smaller the pore spaces, the more slowly the water will flow. So for example, clays have very poor permeability, but very great porosity. So all the pores within clays are so small that the water is basically unable to move through them. So we call clay to actually be impermeable. So rock types like this one, like a cemented sandstone, even though it is cemented, so there's a little bit less space that is able to contain the water, has relatively low porosity, again because of that, but the pores that it does have that are empty tend to be relatively well connected because of the size of the grains. And so sandstone for the most part has low porosity, but it has, or relatively low porosity, but it has pretty decent permeability.